Hello friends, in my previous video I have talked about geosynthetic materials for improving the ground condition and also for improving the bearing capacity of a foundation soil. You can also have considerable reduction in settlement, and if you remember, I have already mentioned that bearing capacity can be enhanced 3 to 4 times. That's a considerable improvement in bearing capacity with the help of geosynthetic reinforcement in any foundation. So, in continuation with that, what are the analytical tools? How we can quantify the bearing capacity and how to quantify the other related parameters. So, in connection with that, this analysis is bearing capacity of reinforced soil foundation, RSF, reinforced soil foundation on sandy bed. The first paper on reinforced soil foundation is given by Binkit and Lee way back in 1975. His famous research paper in the Journal of Geotechnical Engineering is highly regarded. This is the year in which he gave the first hypothesis, and based on that, he tried to calculate the various important parameters. So, if you have a continuous footing or a strip footing, the work by Binkett and Lee was carried out, the analysis was carried out, experiments were carried out on sandy bed, which was reinforced. So, on a sandy bed, reinforced, he has given the analysis based on the experimental data which he developed it. So, we can see he took a strip footing. So, a strip footing or continuous footing of dimension B, and is it is resting here. This is the intensity Q naught if it is unreinforced. Ground or an unreinforced soil foundation. So Q naught is the bearing capacity of unreinforced soil foundation. Now, if the same soil, which is phi soil or granular soil, it is sandy bed, is reinforced. So you will be having with the ground, and this is the footing. So this is the strip footing. So plane strain condition in XZ plane, only the deformation will take place, not in Y direction, perpendicular to the board. And if it is reinforced with geosynthetic materials. Let's say we are putting the reinforcement here. Then the analysis by Winkett and Lee. These are the geosynthetic layer as the reinforcing material. So these are the reinforcement. Layer 1, 2, 3, and the soil mass is there, the soil mass. So this distance is the distance from the base of the footing up to the first layer of reinforcement. Say this is called U, and spacing between two consecutive reinforcing layers, the vertical spacing, you can take it as delta V, and B is the width of the footing. Then this intensity of loading is called Q in reinforced bed. So reinforced soil foundation. So it is called unreinforced Q naught. Reinforced it is called QR. So friends, this is the situation. Now, if you are applying the ultimate load over here, how it is going to fail? Now, it is going to fail if U is the failure mechanism has been given by Binkett and Lee, that the failure mechanism from the experimental data, he could give this failure mechanism. What he observed was like this. Number one, there is going to be shear failure, that is slippage within the soil. Within the soil. What does it mean? That is, shear failure is taking place here. There is a shear lines. So slippage within this is called shear failure. This happens when this U by B is going to be greater than 2 by 3. So therefore, this vertical spacing of first layer is greater than 2/3 of B. And if it is 2/3 of B, the shear failure is going to be above the reinforcement. Therefore, it was observed by Binkett and Lee that the shear failure of soil above the first reinforcing layer. So friends, if this distance is exceeding 2/3 of B, you will not have any interaction of the reinforcing layer. It doesn't improve your load carrying capacity. It just appears that it is a rigid body below and the soil is going to fail. So this criteria which I gave it is called the slippage within the soil, shear failure. Then the second criteria was U by B is not greater than 2/3 or U is not greater than 2/3 of B, but U by B is less than 2/3. So the next criteria was when U is less than equal to 2/3 of rather less than 2/3 of B, and also the number of reinforcing layer is less than equal to 3, where capital N is called number of reinforcing layers. So presently I have shown here 3 layers, 1, 2, 3. These are the reinforcing layers. So if you feel that number of reinforcing layers is less than equal to 3, or it is too short, or it is too short, the length of the reinforcement is not adequate, then what will happen? Then this implies pull-out failure. Pull-out failure. What do you mean by pull-out failure? That means when you apply this intensity of loading QR, your reinforcement is going to be pulled out. The reason being is I have already explained in previous video what is the locus of maximum shear, and from the elastic theory given by Boussinesq. So if you apply the Boussinesq theory, elastic theory, to compute the locus of maximum shear, it is going to be like this. This is the locus of or loci of maximum shear, tau max in xz plane. So this is the locus of maximum shear. So if you take the center line, how this if I have a reinforcing layer here, the reinforcement, the geosynthetic reinforcement placed over here. Now this is the center line. Now the maximum shear is going to be here. So it is going to increase and achieve a maximum value, and then it is going to decrease. So that is the variation of the shear. So at different planes, here you can show it. So the work given by Binkett and Lee is very, very valuable. So here you are going to have the maximum shear. And if you see the vertical pressure is going to be maximum here. And as you go away, it decreases. It decreases like this. So this is the variation of vertical pressure using Bosonic elastic theory. So this line is the locus of maximum shear, and therefore you can this footing, strip footing, which is resting over the ground, can be divided into different zones. This is zone 1. In zone 1, this the soil is going to move in the downward direction. So the direction of movement of the soil mass is going to be vertically down. And this is zone 2. The soil, it will push it laterally. So this is going to be like this. This is going to be like this. This is zone 2. So zone 1, the soil movement is vertically down. And in zone 2, it moves laterally in the upward direction, like this, as shown in the diagram. So this zone 1 has been shown over here. This is the zone 1. So one of the failure is if U is going to be greater than 2 by 2/3 of B, that was the first, then it leads to the failure of the soil mass shear itself. This is going to fail. So that's the one failure mechanism. This is going to fail here. But if U by B, where B is the width of the footing, is less than 2 by 3, or U is less than 2/3 of B, and N is less than or equal to 3, and ties are too short. These reinforcing layers are called ties, are too short, because the soil is going to move in the downward direction as shown in this arrow. This will be pulled out because there will not be maximum grip beyond this zone of maximum shear. So this loci of maximum shear below that, it will be pulled, and therefore the failure is going to be the second type of failure that can happen. And the third is tension failure. So third failure mechanism can be highlighted over here. We can say that third one, failure mechanism, when third failure mechanism is U is less than 2/3 of B, but N is not less than equal to 3, N equal to 4, or it is greater value. So N greater than 4. Good number of reinforcing layers. Long reinforcement, it is not short. Ties are long enough. The length of the ties are long enough. So here the ties which you have put it is long enough. Then what kind of failure? The ties will fail when you go to the ultimate loading condition, and the failure will be tension failure. This implies that failure will be tension failure. So friends, what kind of failure? This will break. That is called tension failure. So we have got three kinds of failure mechanism as per the experimental work carried out on reinforced soil bed, reinforced soil foundation by Binkett and Lee. His research paper is valuable. That's the basic. And he used the strip footing, continuous footing. And he gave you that there could be tension failure, there can be pull-out failure, or if the depth of first layer you are going to have greater than 2/3 of B, then it may lead to the shear failure. So these are the failure mechanism. Now friends, I have already told you that if there is a reinforcement here, you can just see these are the reinforcing layer here. These are the reinforcing layer. Now, the maximum shear lines can be drawn. Locus of maximum shear will go like this. So maximum shear. So here at this point, let's say this point is A. How the reinforcement is going to, the soil is going down. It will apply the force in the downward direction. So in this zone, the zone 1, first zone gives you TD, the tension developed in the reinforcement. So Binkett and Lee paper is very, very important. So zone 1 yields tension developed in the reinforcing layer, which we call it capital TD, tension developed. And we have to quantify it. Binkett has done considerable work in his analysis. He has given us the equation to calculate what is the tension developed, how to quantify it. Now you know the vertical pressure. You see, there is the vertical pressure, sigma V. That you know it by applying the Boussinesq's elastic theory. All of you know it. Boussinesq coefficient Kb multiplied by the load Q divided by depth Z square. So you know it. How to calculate Boussinesq coefficient Q by Z square. That's the value of vertical pressure. And you know how to calculate at any depth. So at any depth Z, this is the direction of the depth Z. And this becomes horizontal distance, radial distance is called r. So tau xz, this is the x direction, this is the z direction, will be sigma v, that is the vertical pressure, multiplied by r by z. This is what you learned in Bosnick elastic theory. So friends, you can very much plot this locus, variation of maximum shear, and you can find out the point of maximum shear. If you join all the points of maximum shear, you will be getting this locus. Point A, point B, point C, you will be getting it. So at A, this is the first reinforcement. How it will behave? Soil is moving like this, downward direction. Here it is going like this, in this direction. So at A, the reinforcement is going to bend like this. So at A, the position of the situation of reinforcement, this is geosynthetics. It will bend like this. There is going to be kink. It is going to bend like this. There is going to be the vertical pressure. There is going to be upward reaction. This is going to create a moment. Two equal forces of same magnitude is going to have anti-clockwise moment. To resist this, tension will get developed. This will have clockwise moment. So TD, tension is getting developed. So that is the situation at A. There is TD. These are the forces that will get developed in all the reinforcing layers, depending upon their magnitude of the vertical pressure. So the vertical pressure in this zone 1, as well as the shearing forces combined together, you can find out, you can quantify tension developed. So zone 1, rightly said in Binkett and Lee investigation, yields tension developed in the reinforcing layers, TD. So TD can be quantified, and it has been given in non-dimensional terms. So we will come to that point later on. So friends, it's very useful expression given by Binkett and Lee in non-dimensional terms. What do you mean by non-dimensional terms? As you know, in zone 1, and this is zone 2, beyond this line of maximum shear, the right hand side, it is zone 2. So zone 2 gives you what? Zone 2 yields what? Pull out resistance. So it gives you the pull out resistance. So the pull out resistance can be computed. It gives you this. So pull out resistance, we can have a symbol T, frictional pull out, F. So we have got two quantity over here, TD and TF. tension developed in the reinforcement. And because of the fact that tension is going to be developed in the reinforcement, the geosynthetic products, geograde, geotextile, are all polymeric material, which has got very high tensile strength. Naturally, it can resist the tensile force. Without this, the soil would have failed in tension. But now you have the reinforcement that can take the tension force. So, friends, how to compute this? So, zone 1, LCO, TD, and the vertical pressure and the shear. How to compute that? The answer lies here. You have the Bosnick equation, and this Bosnick equation gives you two non-dimensional quantity, I and j. So the value of I and j can be seen here over here. This up to point A, this distance, we call it x naught. And as you are saying that the vertical pressure is decreasing, and when it becomes 1% of Q naught, that distance from the center line is called L naught. So there are two quantities now, x naught within the up to this line of maximum shear, and you have got another L naught. So L naught, you can show it up to here, where vertical pressure is going to be here. What is the magnitude of the vertical pressure is 1% of this value, QR. So this becomes L naught. Friends, I hope these points are crystal clear to all of you. So you have got the distances x naught and L naught. And now in the analysis given by Binkwiter Lee, he has talked about I and J. J, Z by B, is a non-dimensional force. It is dimensionless or non-dimensional force. Zone 1 contributes this. So therefore, it is given by the expression Z by B for any depth, Z by B, depth ratio, it is called. It is a non-dimensional term. Z is the depth in meter, B is the width of the footing. So it is the non-dimensional. So J is the quantity, J at any depth. So J, which is a function of Z by B, can be calculated as integral 0 to x naught from here 0 to x naught. This point, this is x naught. This is x naught. So this is 0. 0 to x naught. 0 to x naught. Integral 0 to x naught sigma z or sigma v, vertical pressure, which is a function of depth, dx integrated divided by qr into b, width of the footing. Qr is the intensity of load in the reinforced foundation, soil foundation, RSF. So when you take the strip footing, you know QR, intensity of loading into B is known to you. Sigma Z is known to you. You can integrate. What range? 0 to x naught. You can integrate it. So you will be getting a quantity within zone 1. And there is another non-dimensional force. That non-dimensional force is called I. So I is another non-dimensional force that is equal to tau max. Friends, tau max, you know, it is the shear, maximum shear at this depth. So tau max divided by QR, this becomes non-dimensional quantity. This is the non-dimensional quantity. Having got this, friends, it's very simple to calculate now the value of TD. What is TD? TD is the tension that is getting developed in the reinforcing layers. So when I am placing horizontally my geogrid or geotextiles, I have personally measured. I have guided many PhD students for their PhD work, and they have measured it. You can do it. It's quite easy. So what is the tension that is getting developed? That you can always compute it. Now the non-dimensional quantity are known to you. So Binkwit and Lee has done a considerable work, and the expression given by Binkwit and Lee for the value of TD is very famous. The tension developed friends, the tension developed TD, the tension developed for any depth, you can calculate it for the given number of reinforcing layer N is given by Binkwit and Lee as 1 upon N into JZ J into B. B is the width of the footing minus I into delta V. What is delta V? Delta V, I have already told you, is the vertical distance between two consecutive layer of reinforcement. So it is going to be delta V. Then, friends, you can complete solution has been given by Binkwit and Lee multiplied by QR, the intensity of loading in reinforced, divided by Q naught in unreinforced, the intensity of loading. in a strip footing or in a continuous footing. There is a famous equation given by Binkett and Lee. So Binkett and Lee give you how to compute the tension developed in terms of non-dimensional forces, J and I. And you can calculate it. You can write it in another form. 1 upon n. N is the number of reinforcing layers. So number of reinforcing layers multiplied by J into B minus I into delta V. Now, if you take Q naught here, then it becomes QR divided by Q naught minus 1. There is 1A, there is 1B, another form of computing the tension that is being developed. As the depth is going to change, J value, the pressure will change. The J value will change. Non-dimensional I value will change, which has been given in the form of chart by Binkett and Lee. So you can have the value directly. So these values are given in the form of a chart. So he has developed a chart, and you can get non-dimensional these forces very easily. Now, the tension is also depending upon delta V, what spacing you are going to have. What is the optimum spacing? That's very important. What optimum spacing you are going to have? That's also critically important. So here, what is this QR divided by Q naught? If QR is going to be 4 times of Q naught, my own experimental work, and I have guided many PhD students, more than 100 dissertations at a master level, 10 dissertation at doctorate level. They have quantified it. This is called bearing capacity ratio or pressure ratio. What is QR? Is the pressure in reinforced soil, which is much, much greater than the maximum intensity of loading or the bearing capacity in unreinforced soil. This is called bearing capacity ratio. We call it BCR, bearing capacity ratio. So you can have another form like this, and you can easily calculate, friends, the tension developed in the reinforcement. Now, once you are able to compute the tension developed in the reinforcement, you can provide, applying a factor of safety. You can procure that reinforcing element, geogrid, geotextile, and you will have to see that it doesn't break. So a factor of safety has to be applied. So we will be discussing, there is a long research paper, so I will be further quantifying the pull-out forces, how to compute, how to design, how to analyze the reinforced soil bed in the light of Binkett and Lee research paper. This is widely used across the globe. Any part of the world, people, researchers, they are using it. Friends, it's a very important research paper, without which you can't progress further. In India, at premier institutions, IITs, and others, from where I earned my doctorate degree and master's degree. I worked on geosynthetics. So, in my next presentation, in continuation with this, how to compute the pull-out forces, everything I will talk. For today, it's more than enough. Thank you very much.